Okay, so in this question we have a car moving around down a frictionless track from 1 to 2 and then back up to 3. Now, to begin with, we're asked to work out what reaction force is acting on the car at 2, and then we're asked to work out what is the minimum radius of curvature such that the trajectory of the cart stays attached. So at the point where it gets to 3, it can either go round the bend or it can fly off. And we're asked to find the point at which it just about stays attached. Okay, so for part A, we're going to move between points 1 and 2. And we need to consider the energy balance. So we need our initial kinetic energy, which is 0, it starts from rest. Our work done between 1 and 2 is simply the change in height. So the change in height between 1 and 2 is minus mg y2 minus y1, so the total work done is going to be positive because it's moving in the same direction as gravity. So the total is going to be just under 300,000 joules. And the final velocity, T2, means that the final kinetic energy is going to be half mv2 squared. And that's what we're trying to find, v2. So, this is 0, this is computed here, and we just equate this to this expression, as shown here. Rearrange so that v is the subject, and we can find our approximation for the speed that it will have at point 2. Now, given that we want to find the reaction force that the cart feels at point 2, we then have to take that speed, v2, and translate that into a force acceleration analysis. And at point 2, so remember here we've just come down the track, we started at 1, and now we're at point 2, we're going to have forces of weight and reaction. And the force balance, and we're going to be moving in a circular direction, so we're going to have a normal component of acceleration. So our force balance in the normal direction, Fn, is r minus w equal to m times the normal component of acceleration, an. So r minus mg is equal to m v2 squared over rho 2. Now we can easily make r the subject, and rearranging the known quantities, we can work out that the reaction force is just over 49,000 newtons. Now for part B, the minimum safe radius at P, and remember that we've gone down, and we've got to point 3 here. Again, we're looking for the point, we're going to look at the condition where the reaction force at 3 is 0. So this defines the minimum safe radius of curvature. So we have to do our analysis between 1 and 3 this time. So again, it starts from rest. So the initial kinetic energy is 0, and since it's frictionless, we only need to look at the change in height. This time it's 25 meters. So if we know what the work done due to falling 25 meters is, we can work out that the speed at point 3 should be 22.15 meters per second. Now, if we know that speed, and we know that the reaction force should be 0, then we can work out what the radius of curvature should be in order to meet that condition. Okay, so now looking at point 3, looking at the normal acceleration, so looking at the situation where we're at point 3 and we've got weight going downwards and a 0 reaction force, and we're moving in a circular direction, so we have a normal component going downwards as well. Our analysis of F equals MA gives us mg is equal to m v3 squared divided by rho 3. Rearranging for rho 3, we can show that, using the numbers we've computed before, that the minimum radius of the curvature at 3 should be 50 meters.